The presentation today will be on facade panels from architecture to production. So I will show you a workflow of how we can automate the facade design and some very advanced tools, or how we can create different options, and how we can automate the facade production process. So just a few words about myself. I'm a technical sales specialist at Autodesk. I have a master in civil and structural engineering in Romania. I'm currently based in the Dubai office. I moved to the Dubai office from Singapore. I spent there about 5 years as a consultant, helping large organizations to implement BIM technology, cloud technology, VR, and automation. I have more than 13 years experience in the AEC and information and technology sector, and I'm happy to share some of the knowledge and some of the experience that I accumulated during this time. So today we're going to have plenty of topics to discuss. I just use this keyword slide to see some of the topics that we were going to touch. So facade design, architecture, we will look into fabrication, optioneering, dynamics, 3D printing, panels, different types of workflows. So in this class, you will learn how to create optimized concepts of facade with Dynamo Studio and Formit. You will learn how to explore options for facade panel layout with Dynamo Studio and Project Fractal. You will learn how to create dynamic panels on a complex facade with Dynamo and Revit. Also, you will learn how to link the final design to fabrication using different technologies for 3D printing, also for assembly of parametric systems. So let's start. For this particular presentation, we have created a project, which is an airport project. And it's a fictional project, but it can be a real project as well, which we try to be as much as possible to the reality. It looks like this, so it has 2 sections, 2 pavilions, and we will focus mostly on the facade design and how we can customize this facade. So some of the challenges that we have for panel design, fabrication, during the fabrication phase, during the design phase, some of the challenges is that many times we have non-economic solutions. We have also aesthetic. We need to hit the right balance between aesthetic and functionality. Also, we need to optimize the facade layout. And also, we have geometrical constraints. It's easier, for example, to have straight panels. The moment we have a bending or we have a double curvature, those panels are more difficult to fabricate, and they will involve more cost. So speaking of fabrication, some of the challenges is panels don't fit on site. So you have one thing in the design, when you go on site, you realize the panels don't fit. Also, materials cannot handle design planar deviation. Also, we want to avoid as much as possible custom fabrication. Custom fabrication involves more work, involves more cost, more resources. And also the production tables don't follow easily for assembly of non-planar elements. Basically, the production tables that we have, they are very optimized to create flat panels. The moment we start to deviate from that flat panel, we need to complicate things and involve more effort. So some of the project goals, we want to define a facade layout with optimal grid divisions. We need to find an optimal grid for this facade. Optimize the facade panels driven by an external influence. It can be a solar installation, or it can be a mathematical shape. We can use like formulas and equations to create parametric architecture. So another goal is to reuse the digital data for facade prototyping, for 3D printing. So basically, we can even create mock-up models of the facade using 3D printing. And also, what we need, another goal is to link the design process to the fabrication process. So we have a continuous flow of data from the design process all the way to fabrication. These are the 4 major goals, and let's see how we can achieve that. So one of the main consideration is that we need to specify what is the planar deviation of this panel. So ideally, we need to have a flat panel, but for this kind of organic shapes, it's not always possible to have flat elements. So we have to come to an agreement how much we can deviate from that planar shape. Also, we want to verify the panel rectangularity. Building a rectangle frame, it's much easier to fabricate than having to measure the different distances, and the moment the panel becomes non-rectangular, it will involve more effort. Also, panel surface is limited for handling during fabrication, so we try to minimize and make the process of installation more efficient. So, in order to achieve this, we have 4 phases. We split the design in 4 phases. First one will be facade layout definition. Second phase will be to panel placement. We place the panels. Third phase, we can do the prototyping. By the way, this is an optional phase. It's only if we want to have like a more marketed design, we can show to the customers a mock-up version of this facade. And the last step, phase 4, will be panel fabrication. These are the steps that we need to do. So the same steps that phases that we need to do, and we summarized the efforts that we need to do and the task that we need to do. So in the conceptual design phase, we need to sketch the geometry, create logic to optimize the panel distribution. Also, we need to optimize and create options for the building concept, and also take the fabrication requirements into place. Also, the detailed panel design, we need to apply computational logic to be able to apply these panels automatically. We can create several design options. Also, we can use solar analysis. Also, moving forward, we have panel prototyping. So basically, we can create a 3D replica of that. And for the facade panel fabrication, generation of digital deliverables. So basically, we want to have the design information, move it into the fabrication automatically, and just create all the bills of materials, all the fabrication drawings automatically. So this is the summary, and these are the tools that we have used. So basically, based on those tasks that we need to do, this map shows you how we can use different products, Autodesk products, in order to achieve that. So in the conceptual design phase, we use Dynamo Studio. We use Autodesk Formit, which is for conceptual design. We also use Dynamo Customizer, and we are using Project Fractal. So it's another product that we can utilize for design optioneering. After the concept, you can see that we can use Revit all the way to the fabrication. We will use Dynamo for automation. Also, we can use 3D Studio Max for visualization and rendering. We can use Fusion 360 as well to create a ready-made model for 3D printing. Sometimes the architectural models that we design are not always printable, so we can use a very simple design tool, Fusion 360, to create a 3D printing ready model. Optional, we can use Inventor also, and we can use also third-party software by facade fabricators and producers. In this case, we have used ShoeCAD, ShoeCal, and ShoeCam. Okay, these are 3 products that they each have a certain role in the fabrication process. Of course, this is just an example of how we can use Autodesk tools to design it, but of course, some of these products can be changed and replaced with others. Or some of the steps, of course, can be skipped. So for example, if you don't want to do the 3D printing, you don't need the Fusion 360. You can just move from Revit directly to these 3 products. So phase 1, facade layout. Okay, so these are the steps. We will start with the setup layout. Then what we want to do using Dynamo Studio, we can check the fabrication readiness. So basically, we can have different color codes for panels that are easy to fabricate, panels that are not so easy to fabricate. And we can decide what are those parameters that decide that a panel is not easy to fabricate. So we have full control over that. Another way is to use Dynamo Customizer, so we can explore different options. And we can use Project Fractal for layout optioneering. Now let's see how this works. First step, we need to create a SAT file from the building mass surface, create the grid geometry-based surface, custom fabrication readiness verification, results representation, and send that to the cloud. So you can see these are cloud products. Whenever you see this sign, it means that it's a cloud product. So we can create the shape of the building in different tools. You can use any tool. As long as that tool can export SAT, you can import that geometry inside Dynamo Studio, and you can start to apply automation. In this case, we have used Formit to create the SAT file, but of course, as I said, you can use other platforms as well. Okay, so this is the Dynamo interface. I know it looks a bit complicated, but it's actually broken down into several steps, and each step of Dynamo is performing a different operation. So Dynamo is actually visual programming tool. Basically, you don't see any scripting there. You see nodes. Each node is performing a certain operation, and it's outputting a data. That data, we can feed it into a new node that can perform another operation. So we link this thing together until we get something, a result. In this case, the first nodes, they are designed to read information from an external source, in this case, the SAT file. So basically, we are bringing the surface of that conceptual building, we are bringing it inside Dynamo. After that, we are starting to feed information here, so the goal is to split the surface into horizontal divisions and vertical divisions. Okay, so we can specify the U and the V of the structure of the facade, so then we can see a list of panels with all the points, placement points, and all the sizes. Next step would be, after we generated this layout, horizontal, vertical division, we need to calculate if these panels are, first of all, rectangular. So if the angle between the two intersections there is 90 degrees, or more or less, and how much it varies. And another thing we need to check, planar deviation. So we need to check if the element is flat or not. So we can have different nodes there that we can use to do that. And in the end, we can use color coding, you saw there, to color the panels that are rectangular and easy to fabricate. Planar deviation is 0 or under a certain limit, so we can specify the planar deviation. If it's higher than 5 millimeters, highlight that panel, and it means that panel is more difficult to fabricate. So in this case, we just test one option. This green panels are very easy to fabricate. The red panels there are more difficult to fabricate. Meaning that in this situation, this design option has, let's say, about 15% of the panels which are are more difficult to fabricate. Now, the goal is to try different options, and you can use computational design to try multiple options until we find that layout which is optimal. Okay, so we can move to the next step. After we create this script, we can actually share this with external stakeholders. So we can publish this script. We can publish it in the cloud platform. So just use publish. We can log into the cloud account. And this cloud platform allows that Dynamo script to be controlled. So it takes all the inputs, all the slider inputs from the Dynamo script, and it allows us to test different options using the cloud. And we can very easily share this link. So we can just share the link to external stakeholders until we find the option that is the most suitable. So basically, we are using a web-based interface to control the different options. So we started from Dynamo. Now we are in Dynamo Customizer. So this is called Dynamo Customizer, which allows you to explore different options. Okay, now we can go one step further. And what we need to do is the facade layout optioneering, okay? So in this case, we will use another tool. I think it's, yeah, so you just have to type home.fractal.live. So this is what we call Project Fractal. So Project Fractal can read the information from Dynamo Customizer. In a way, it's similar to a Dynamo Customizer, but it's giving you more option. And you can control not only the inputs, you can control also the outputs. Okay? So until here, we have inputs, input values. So basically, we can input how many vertical divisions you want, how many horizontal divisions you want. Also, we can input the size of the panel. And here we have results. Okay? And Project Fractal is using the power of the cloud to compute different options. Okay? So we can choose from a range of solutions. Okay? So say, I want to have for 10 rows, for 12 rows, for 20 rows, combine that with 20 vertical rows, 25. So we can do all these hundreds of combinations using the power of the cloud. We are not relying now only on our desktop. We can actually use the power of thousands of machines that can perform this in an idle mode, so we don't have to care about the time when this is processed. So it's much faster using this. After we are generating the number of solutions based on different combinations, maybe we can have like hundreds of design options. Then we need to start to select the options that are the most suitable for us. So how do we do that? Is by filtering the results. Okay? So in this column, for example, we have the maximum and the minimum angle between the mullions and the parts that are connecting. So I can say, I just want to have maximum 84 or 85 degrees. Okay, if the angle starts to become bigger than that, I don't want those options. So I can filter them out. So basically, I can choose a filter here. Now, I already eliminated hundreds of designs that are not usable. Then we can apply another filter. Let's say I want planar deviation less than 5 millimeters. So again, I can filter here only the ones that are under 5 millimeters. So Project Fractal is actually a tool that is used for design optioneering, and it can help us choose the best design. So if you look here, we can see how we can filter the results using different filters. This is giving me all the combinations there, but I can filter them by using those sliders. So let's look on the results. I can open the same script using Fractal. And these are all the hundreds and thousands of possible combinations. And then here I can choose just the one that have planar deviation less than 10 millimeters, for example. And here I want the maximum panel height between this range. And it's narrowing down the results. And you can see it selects only green options. So this one only has 4 panels that are difficult to fabricate. So this is how we can use the power of the cloud to identify the best solution. So we can optimize our designs and reduce the waste and also find the best fabricatable solution. Okay, so this is Project Fractal. After we decided on the best output, we need to continue for the conceptual design. So we need to apply this facade on the actual building, and we need to see how it looks like. So at this moment, we have only seen the facade. Let's see how that connects to the rest of the building. So for that, we can use a product called Formit. Formit is also linked to the cloud workspace, and it can read this customizer, this Project Fractal solutions and automations, and we can use it to apply those on the conceptual geometry, conceptual mass geometry. So let's see how it works. So now we are in Formit. Formit can read the scripts that we have done in the cloud, in Project Fractal, and we can take those scripts, generate the facade based on the best and most optimized design option, and then we can just place it on the building. So this is where we can place it. Also, we can mirror it, and also we can even change values. So we can explore also different options, you'll see different layouts. So this is called Project Formit. Okay, phase 2, panel placement. Okay, so after we have created we decided on the general concept of the building, we can start to do the panel placement. So basically, we can use a tool called Revit, where we can bring the conceptual mass from Formit. Then we can create an adaptive component, adaptive family. We can use Dynamo to place those adaptive families on the layout that we have just created. So let's see how we can do that. Okay, so in Revit, we need to go create some custom families. So what we want to achieve is actually this kind of effect. These panels, seen from the top, they can have different height and also different elevation here of the opening. So we need to create this family that has this parameter flexible and also has this parameter flexible. So we can stretch it, and this one we can stretch it, okay? And then we will use a Dynamo to close and open this opening. So we can use equation, so like a sinusoidal equation, or we can use like a solar study, for example. So let's see how we can do that. Of course, in Revit, we can customize, we can create different types of detailing. So we can have one family for for solar analysis. We can have one for 3D printing. So if you want to 3D print that, you need a full block. Also for fabrication details, you need a family that is more accurate. So we can create 3 options, and we can customize them. All these families, adaptive family needs 4 placement points, okay? So from the grid that we have designed in the previous steps, we can reutilize the same script and determine the 4 placement points of this adaptive family. And this is the adaptive family. It also has 4 placement points. So we match those 4 placement points. We will match those 4 placement points to the grid layout that we have created here. Okay, so to do that, as I was mentioning, we can reuse the facade layout configuration script. We can extract the corner points from the quad panels. We can evaluate the fabrication readiness, so we can see which panels are difficult to fabricate, and then we can place the panels. Okay, so to do the fabrication points, I won't go into all the details of the script, but just to give you an idea how it looks like, we can actually run the script using Dynamo Player. So Dynamo is also part of Revit, and it has a Dynamo Player. Basically, Dynamo Player can read the inputs and can create an interface that is ready to use in Revit. So again, I won't go into the exact details of this. Of course, everything can be organized into groups of nodes, so we can easily debug the nodes. First step is to read the facade. So after we brought the mass geometry from Formate inside Revit, we can read the facade, bring it inside Dynamo for processing. And we can reutilize the same nodes, the same script that we have done, we have used in the concept phase. We will just have to improve it. We will just have to add more information, more nodes that will allow us to detect, to extract those 4 placement points. So for each panel, basically, I will generate a list of 4 points, placement points. After that is done, I can move to the next step. And I can start to place the panels. Okay, so this is where we can start to place the panels. So, of course, first, using Dynamo Player, which can read that script, we can directly from the Revit interface, we can generate the layout. And we can turn on and off, create the panels. So when we are studying the different options, we won't place the panels because it will slow down the process. So first we optimize. Once we find the optimized layout, then we can turn on this button and we can start to place the panels. So this is from one click from Revit, we can just place the panels automatically. So basically, what we have done, we have made those adaptive families. We matched them to the same pattern of the conceptual layout of the facade using Dynamo. Of course, we can select another facade and we can add all those panels automatically. So we can place, in this case, hundreds of panels in one click, okay? And if we want to see only the shape of the panel, we can choose between different geometries. We can have just the rectangle, or we can have the full geometry of the family. Okay, let's move to the next step and see how we can actually customize the facade by controlling those height and width angles that values that I was explaining. So now all the openings and all the extension of the panel is constant. It has a nice effect But why don't we go a step further and use mathematical formula to drive the geometry? So in this case, we can use a sine wave-driven panel dynamics. So basically, we can match according to this line of the panels. We can create a sine wave, and we can match the height of this sine wave to the opening of the panel. So basically, I'll show you in the next slide. You will understand a bit better how this works. So we can take this delta Z value and match it to the opening of the panel. So then the panels will have like a nice wavy effect. Also the same value, we can match it, we can map it to the extrusion, to the extension of the facade, so we can have a very nice 3D effect. So again, we start after the panels are placed. We need another script. We need another Dynamo graph. So we open Dynamo again. We can take part of the existing script. We can reuse it. Again, we just have to input some new nodes and new information. And here is where I can get the horizontal points of the panels. Basically, I can read that information from the panels which are already there. And the next step would be to create a sine wave. And of course, all this is customizable. So basically, we can choose how much height will this sine wave have. So I'll just move a bit faster. Okay, so these are the sine wave that we have created. So we can see them also in Revit. And then measuring this distance, I can make that into the opening of each panel. So we need one more step, is to produce the final effect. So we feed the information where it's required. And then we can generate the sine effect. Okay, so after we have designed the script, we can execute it, and this is where now it's applied to the facade. And you can see now the facade, it's having this sine effect. So this is on horizontal view. But if you look on the side, is also from the side, it has the same effect. You can see here from the side, you can also see that the facade is also changing the shape. So this is the end result. This is what we can do using automation. Also, another option would be to use solar analysis. So we can do a solar analysis of the facade and influence the opening of those panels. Basically, if some panels are more exposed to the sun, we can close them more. We can close them. We can make them even totally closed if you want. So we can measure the amount of light that can come inside the building. And we can create a solar study using color codes. These color codes, they are mapped to values, certain values. Those values can be mapped on the facade opening. So basically we are using external influence to drive the design. So this is what we can also do using the power of computational design. So these are the steps. Again, I won't go into very technical details. Basically, we can perform a solar analysis, then compare the calculation points. So for each panel, I will detect the amount of light that comes in. That will give me a value. That value will determine how much the panel will be open or closed. And the effect will be this. Let's say we are using exactly the same script. We will change the final part. And these are the points located on the facade. Each point has a value of how much sun exposure is there in that position. So now we are matching the values of those points to the panels. So let's see the effect. So this is the final effect, where you can see that the panels which are more exposed to the sun, they are more closed. You see the opening is quite small. Here it becomes bigger. So they are more open because they are shaded. So there's another way of using external sources, external intervention to drive the geometry. So we are not constrained now just by human design. We can actually use the external conditions, the sun influence, in order to create a sustainable facade. Of course, we can also apply like heat maps. So we can even color them. We can color the facade elements, and we can start to prepare for the 3D printing. So this brings me to my next step, where we can create a mock-up of the facade. We can create a 3D printing version of it. So for 3D printing, we can have different options. Depends on what type of printer we are using. You have seen some 3D printers here in the lobby. Some of them are using plastic, some of them are using gypsum. Depends on the capabilities. We can prepare the model so it can be ready for different kinds of printing techniques and printers. So if you want to see how the 3D printing process is, to simplify it, it takes the object, it slices into layers, and then it starts with the build piston here, and it's adding layers upon layers. And it's going down, and it keeps adding another layer, until it creates the entire object. This is one type of printer, but of course we have different other methods. So for this example, we use this kind of technique. One more thing that we need to consider, as I was mentioning, not everything that we design in Revit, it's printable. So we need to, because there are some, for example, openings, or the object has to be a continuous object. You can't print voids, for example. You need to have something that sustains that void. So we need to do some preparation for that. So in order to do that, we can use a product called Fusion. Basically, we can export the geometry from Revit using SAT format. It's very easy to find the export functions in Revit. Export as an SAT. And now I can bring this file inside Fusion. So Fusion 360, it's a cloud CAD, very powerful tool that enables you to create geometry very intuitively. So this is how the model looks like. So some of the things that we need to do, like for example, this roof, the top of the roof, it needs to be thicker. Some printers, they have a limitation. They cannot print very thin surfaces because they will break. So we need to thicken it. Also, we need to join some of the objects. It's better to have like an entire surface which is joined instead of having like different bits and pieces. In this way, we will have just one single object, and the printer will know how to handle this. The functionality of Fusion is quite intuitive, and you can just drag and drop. If you want to extend the surface, you can just drag the surface and extend it, so it's very powerful to do that. Another customization that we want to do here, you can see there are some openings. There are too many surfaces. The 3D printer will not know how to handle this. So basically, what we want to do, just connect all these lines and create like a very nice thick surface, which can be very easily processed by the 3D printer. So, of course, this is just an example. You can use Fusion, you can use Inventor, you can use any other tool that can read an SAT format or that can read information from Revit. Okay, so now we have a nice 3D object that we can export as this time STL format. So remember, 3D printers can read STL format, and Fusion 360 can very easily export the STL format. Of course, we can add some materials, and then we can move on to the printing process. So this is how the printing looks like. This is how it looks for the monochrome. This is a monochrome printer, by the way. So it's printing just one color. As I was showing you, it's printing layer by layer. And it goes all the way through, and it adds layer by layer, until everything is printed. So last step, and now we just need to remove the gypsum. This is by the way, a gypsum printing. So we just have to remove the excess gypsum, which is not hardened. And this material can be reused for a different printing, for example. And we can even use printers that can support color. So depending on the budget, of course, printing in color will require a bit more cost. Or you can print it in color or in monochrome. This is how the final product looks like. And first example is just using the concept geometry, like the shape of the airport, but we can also print the facade. So if you want to focus on the facade, we can again export to STL format. And now we can use Dynamo to export to STL. Dynamo is very powerful to export this kind of format. And again, we are doing the same process, the same steps. So in this case, I want to reduce, this part is not relevant, I just want to focus on the facade. So I can very easily remove it. And I can even produce like a mesh of that object. So this can be exported as an STL format, again, for printing, so we can just print the facade. You can see it's very easily to cut. You just take a plane, you drag the plane, you can cut the object very easily. This would be a bit more difficult to do it in Revit, or if you want to do it in AutoCAD. So having this tool, it's very powerful. It's actually a very powerful tool to create any kind of object. And then, if we look at the result, here we go. So this is where we have printed only the facade, using that sine formula. Okay, this is the final product, and we can even color the openings with blue color, so then the sine function effect will be more obvious. And this is another version that we used. So here we used the solar study. So we overlap the solar study to the geometry, and you can see where we have shade, the panels are closed, here are more open, and it's combining the both the sine effect and the solar study. So we can play around and we can explore even more options. Last phase, panel fabrication. So we have seen the tools that allow us to explore different options. We can combine different design options, solar study, external factors to drive the geometry. Now we come to the last step. Last step is very important, is the fabrication step. So for this example, we have used 3 products, as I was mentioning, ShoeCAD and ShoeCal and ShoeCam. By the way, this is a German company which is doing this kind of tools which are directly linked to their custom facade elements and facade panels. So ShoeCAD actually, it's a plugin for Revit. It contains architectural libraries for Schuko parametric systems. It can be also a plugin for Inventor, so it automates the creation of parametric system assemblies based on the data exported from Revit. So basically, you can design the panels in Revit. Using this ShoeCAD, you can actually generate the exact fabrication panels. So it's a plugin. ShoeCal is also, you can use it for 2D and 3D calculations. You can create quotes, job planning, purchasing orders, delivery and innovation, saw controls, and many other functionality. And ShoeCam is a software to control CNC machine based on fabrication data. So basically, this tool talks to the actual machine that fabricates the panels. So it's a combination of all these 3. We start from Revit and ShoeCAD, then ShoeCAD to Inventor to generate all these small parts. You know very well for a facade panel, there are hundreds sometimes of pieces and bits and pieces that we need to consider for fabrication. This tool actually handles all that and can generate all those bits and pieces. And then it produces some documentation, material list, can be transferred into the ShoeCam, and you can just automatically produce them. So let's see at the process. First step in Revit. Revit is now the source of data. So we need to feed this data inside the fabrication tool. So in this case, we just selected a number of panels. You can select all of them, but for this example, we just selected a number of panels. We can export them, use the export function, and we can bring them inside the ShoeCam tool. It's actually using a database format. So it's an Excel format which has all the parameters of those panels. These parameters can be brought inside the fabrication tool for customization. And this is how we can generate the fabrication drawings automatically using ShoeCam. Basically, we take the same database file, and we can generate. We just press OK, and it will generate. It's actually TXT files that have embedded all the fabrication lists and bills of materials. And we can even preview how the panel looks like. And as I was mentioning, it has all the details, all the fabrication parts. So if you look at it, even the brackets, the bolts, everything is generated by ShoeCam based on the information that came from Revit. So now there's no disconnection between fabrication and design. You can take the data from design and drive the fabrication deliverables. Okay, so this is how we can create the solist and the materialist. So once we generate the geometry, also we need to produce all the solists, all the parts that will be fabricated. This is how it looks like. You don't have to know all this interface. There are specialists who are experts in how to read this information, and they have the right training to understand all this data there, and they know how to manipulate it, so they have the right results. And the last step, fabrication. So it's all automated. They have the machines that can read those file formats and can, using robots, they can cut all the profiles, weld them together, drill the holes where they are supposed to, and assemble them together. So it's still, you can see, it's still using manpower. I said still, but who knows, maybe in the future this will be all fully automated, and we can focus more on the design, and also the fabricators can focus more on the controlling the machine than having to do all these things manually. But it's quite impressive. You can see all the bits and pieces are brought to the assembling table, and then they just have to screw the panels. You can see they can use cranes that can place the panels, and they can fit exactly into the right locations without having any deviation. And this panel is ready for installation. We can also use the ceiling, so we have waterproof systems that can be treated. Of course, they have all the technology, so these facade panels are ready to use and at a good quality. Okay, so conclusion. We started from, just to recap everything, the process, we started from just a basic script, then we used Dynamo to generate that, then we used Project Fractal for optioneering. So basically we are using it to filter the results. After we found the best option with the best fabricatable profiles and panels, we have attached that to the concept model using Formit. We moved on in Dynamo and Revit to create the placement layout. Then we used adaptive components, adaptive families to build a facade. And then this is how the facade looks like. And then we add a bit more complexity. We have created the 3D printing model. This is where we prepare the model for fabrication, 3D printed the model, layer by layer, remove the excess material, and there we have the mock-up of the facade. And we are preparing for the last step, where we took the data from the design and we converted into fabrication-ready information. We have the right tools that can generate all the bits and pieces that are necessary for fabrication. And after that, we have generated the bills of materials. All that went straight to the machines that can fabricate it. And we have the ready-made product which can be taken and installed. So using technology and automation and the power of the cloud, we have achieved amazing fast results by using these tools together. So this was the presentation. If you have any questions regarding what you've seen, or any observation, any comments? Did you like it? Okay. Did it inspire you? Okay, thank you. So I know some of the things might look complicated. Of course, even AutoCAD looked complicated when I first opened it. You need to have the right people, the right skills, but the tools are there, they are ready to use, and the future is not there yet. The future is actually here, the tools are here. So I hope it was inspiring, and thank you very much for your attention. Okay. Thank you. Teşekkür ederim.